Thanks so much for having me. Yeah, I'm Parastoo. I'm really excited to be here. Thanks for the introduction. I'll be talking about that project, so you'll hear more about it. Um, so today I'll be talking about some of the work I've done mostly during my PhD when I was at Stanford. So now I'm at Princeton. We have a growing HCI group there with a brand new logo, if you haven't seen it before. But I just wanted to kind of acknowledge that a lot of the work that I'll be talking about today is actually work I've done at Stanford during my PhD. How many of you have tried a VR headset? Okay, everyone. How many of you own a VR headset? How many of you have used VR outside of gaming? Okay. Okay, quite a few. Okay, so this is why I'm quite excited about the line of work around VR. Obviously, VR has been around for decades, but it's the commercialization of the virtual reality hardware that's making it an exciting time to work in this space. People such as yourself mostly have tried VR and are excited about the future of interaction in that space. But I want to start off with, I saw a lot of hands when I said used VR outside of gaming, but that's quite rare. So I'm assuming you used it in research context. Is that right? Okay, a lot of nodding. Yeah, I feel like people usually, if they own a commercial VR headset, they think of gaming as primary application. So I like to start off by some examples of what I think VR is great for. I think VR is great for experiences that are not accessible or affordable for people, or experiences that are flat out impossible. I would not be able to experience what it's like to be in the International Space Station, but you can do that in VR, and especially with photorealistic rendering, that experience is a lot more closer to what we used to have, what we could have. Creating any 3D artifact, 3D products, animations, it makes a lot of sense to do that in a 3D environment if you have good interfaces and interactions. And finally, education. Here, I'm showing an example of manipulating a 3D molecular structure and creating it. And this really takes advantage of our innate spatial reasoning skill. And there's lots of applications in education and training for things that are either unsafe to do or dangerous to do before you're fully equipped to tackle them, like for firefighters and other contexts. Yeah, so visually we see a lot of exciting content, but when it comes to our sense of touch, at best what you've probably experienced is holding, unless you're doing haptics research, is holding a controller that vibrates in your hand once in a while. So there's really this gap in commercial VR's haptic rendering in terms of what we can feel and manipulate. But when we think about how we interact in the physical space, when we touch objects, when we touch surfaces, we feel their texture. When we grab an object, we feel its weight. The force feedback that we receive actually allows us to improvise in our interactions with physical objects. And all of this textures and forces really enable dexterous manipulation, things that we can't do in VR currently. So what happens in VR headsets, if you put on a headset, you see some virtual rendering, but when you reach out to touch it, if you're holding a controller, you'll feel a vibration, but otherwise there's really nothing there for you to grasp and manipulate and experience in that way. So I started my PhD with this kind of out there potentially idea of what if we had a swarm of drones that moved around and kind of acted like puppeteers of this physical interaction, this haptic interaction. And this was a time where drones were really becoming smaller and more affordable and becoming really popular. So it wasn't so far-fetched to think that that trend would grow at the same rate at the time. And so the idea here was, what if we had these small drones in our spaces, and when there was a virtual object that we wanted to interact with, these drones would move around and look for either 3D printed physical objects or even everyday objects that could be a proxy for that virtual object, and then would bring that object to us so that when we touch a virtual object, there's actually something physically there for us to grasp and manipulate and leverage all the rich experiences and dexterous manipulations that we can do with physical objects. So this is what I set out to do at the beginning of my PhD. And I'll give you an example of how this could be used. Imagine you're doing, this is an e-commerce application, you're doing some virtual reality shopping. When you buy a piece of clothing, you actually want to be able to feel its texture, its weight, and things that are currently missing in what you visually would see in VR. So the idea here is, what if we could feel the texture of the virtual fabric that we're purchasing, or the weight of the material? So I set out to do this. I started with just one drone. This is a custom-built racing quadcopter that I've enclosed in this meshed cage, so that when you make contact with it, you don't touch the propellers, basically. And we integrated this with the e-commerce application that I showed earlier. So we were tracking the drones, the user's head, their hand, and then sending waypoints to the drones to autonomously fly to the next potential interesting contact point, and allow the person to actually feel some texture or weight or other types of haptic feedback. So this is a video of me actually trying this application. So here we have a 3D printed hanger attached to the drone, and there are different textures and fabrics around the drone. So depending on the fabric you were touching, you would feel silk or other textures. And as you saw here, this didn't work so well. And the reason is, you have this drone that there's airflow, but then it's also enclosed in a meshed cage that's interfering with that airflow. You have all sorts of fabrics and 3D printed props attached to it that makes this actually a really hard control problem to have the level of precision that we need in terms of how the drone is positioned in space. Because you're in VR, you actually aren't seeing the drone. So that accuracy needs to be so, it needs to be so precise that when you actually make contact, the drone is there with the right form of texture or object. So this was the challenge we had with this project, and this is not unique to this specific haptic device. All haptic devices, whether they're a controller that you're holding, or a wearable glove, or encounter type haptic devices, which is these categories of devices that were traditionally grounded robotic arms, but the case of the drone would be an encounter type haptic device, because as the idea is that you're not wearing anything, you're not holding anything, but as you touch a virtual object, you encounter the end effector of the robot. So all of these devices and other forms of haptic devices have limitations, whether it's the accuracy of if it's a encounter type haptic device, where it can be positioned in space, whether it's in terms of like precision of where the haptic sensation is presented. It could be speed issues if it's an encounter type haptic device, or if there may be some delays in the haptic rendering, and as well as resolution. So if you're rendering some 3D mesh, there may be limitations in terms of the resolution of the display. So the kind of insight that I drew on in my work was that you don't need to have perfect hardware, because we are not perfect. We don't have perfect perception. And so we can leverage that limitation of our perception to make these hardware devices appear as if they work better than they do. So I'm going to ask everyone to try this. Try to touch your 2 index fingers together above your head. Just one try. You get one try. Okay, I think some people did more than one try, but great. So if you're in front, you maybe are relying a little bit on your peripheral vision. But if you really do this above your head, it's really hard to estimate where your finger is in space without looking at your finger and actually making contact. And this is an example of a limitation of our perception. What you're relying on here is actually your sense of proprioception, the forces in your muscles and joints telling you about the position of your finger in space. And that's a pretty noisy signal. We don't actually have a very good sense of where our bodies are relative, our limbs are relative to each other. But our vision is more accurate, which is why some of you were trying to kind of bring the finger forward and look at your fingers. So this is what I mean by we can leverage these limitations of our perception to make these devices appear as if they work better. And so today I'll talk to you about how I applied this kind of idea to 3 projects. One for making the drones appear as if their accuracy was better. We also worked with tabletop robots, and there we were addressing the issue of speed. And also with these devices called shape displays, which are matrices of actuated pins that move up and down. And because of affordability and other considerations, they're actually potentially low resolution. So there we were addressing the perception of resolution in these displays. So today I'll talk about these three projects, which are all in the kind of realm of creating this illusion of realistic haptic rendering by leveraging our limitations of perception. And then I'll talk about what we can do if we are okay with kind of breaking that sense of illusion of realism and really leveraging the fact that we can do things in mixed reality beyond what is possible with our physical spaces and physical interactions. And so I'll talk about the project that Stephanie mentioned, as well as some framing around this idea of beyond real interactions in VR. So I'll start off by the first project, going back to the drone project. So as you saw, we had that safe to touch drone that we made, and we attached fabrics to it so we could do some level of texture rendering. We could attach props to it so we could animate those props. And also the box itself, the drone, could act as some sort of a box that could fly and land on different surfaces. And that itself could be some sort of object that people could manipulate. So at this point, you may be wondering, would people even feel comfortable being that close to a drone? If you've ever interacted with a drone, you may not have wanted to be that close, let alone touching a drone. So before doing this project, actually, we ran a study. This was a between subject study design. So we had a group of participants, half of them interacted with an earlier prototype of our safe to touch drone, which was covered in a mesh cage. And the other half interacted with the original commercial drone that didn't have the mesh cage. This was an elicitation study. So we didn't tell people what to do at all. We just showed them these visual prompts of different tasks, like make the drone take off or land, go further, take a picture, etc. So we saw in the case with no cage, people used gestures, voice, their hand gesture, voice, and other ways of kind of interacting with the drone. But more than half of people in the safe to touch condition with the meshed cage actually instinctively went up to the drone, grabbed it, moved it around, for example, picked it up to make it take off, or tapped it to make it land, and things like that. So this was encouraging that maybe if you have a safe mesh around the drone, people would feel comfortable to some extent to be in closer proximity to the drone. So let's go back to the problem that we were trying to address. So ideally, if everything was working perfectly and we had perfect accuracy, as you were reaching out to touch a virtual object, like a virtual piece of fabric, the drone would be precisely positioned in space so that you would make contact with the right piece of fabric on the drone. But the issue we had was that sometimes the drone would be slightly offset. And even with the tracking that we had due to the cage and all the props and fabrics attached to the drone, it was really difficult to always have that level of precision that we needed. And more importantly, or more problematically, the drone sometimes drifted during the interaction. So to address this issue, we actually drew inspiration from this work at CHI 2016, where people were presented with 3 virtual blocks, but there was actually only 1 block. And so the researchers here were retargeting the user's reach so that they would feel as if they were 3 blocks. So we were inspired by this work. Has anyone tried this demo at a conference? One person? Yeah, if you try this, you would know that once you take off the headset, it's a very magical experience. You're very surprised to know that there was only 1 block in front of you. And so the idea here was that we wanted to better understand how this magic trick worked so that we could apply it in a more dynamic context where the user is not stationary behind the table, the block is not this static cube at a specific distance, but it's a drone that's actually moving throughout the interaction. So we were wondering, how can we apply this form of retargeting in a more dynamic setting where both the user and the drone are actually in motion? And to do this, we had to go back and kind of look at how the brain plans and controls movement. So let's think of the very simple case of you wanting to reach to touch an object. So how this works is that your intent is converted to a motor command that is sent to your body, and that leads in your arm actually moving forward. And your body needs to have a way of estimating its state, like what actually happened due to this motor command. So it uses the sensory apparatus, your vision, proprioception, all the other sensory signals that you felt as you were moving your finger. Those are used to help the brain kind of estimate its state. It then uses, it compares that to what it expected to happen, and then that difference is used to kind of update the motor command. And this is basically saying that the brain, it kind of operates as optimal controller here. And this is really what we're leveraging with this kind of retargeting. And how we apply it here is that as you're reaching out to touch the object, if the drone drifts to the left, we actually, at the same rate, drift your virtual hand to the right. Keep in mind you're in VR, so you actually can't see your real hand. And so what happens is that the brain visually sees the hand going further right than it expected. So it updates the motor command to shift your hand further to the left. And if this discrepancy is small enough, what happens is that you end up making contact in the physical world with the drone at a slightly different position than your virtual hand does with the fabric. And if it's small enough, you won't even notice that this is happening. So this is kind of the illusion of retargeting in this case. And the reason this works is because of kind of this limits of our human perception. Now I want everyone to try the same task, but instead of above your head, in front of your view, try connecting two fingers. You get one shot. I think everyone was successful. And this is because your vision is actually less noisy than your sense of proprioception. So the signals that are coming in this case of retargeting, are both proprioception and vision. And the brain knows this. The brain knows that proprioception is noisy and more uncertain. And as a result, it weighs vision over proprioception. And this is known as the visual dominance effect. So if there's some mismatch between what you're feeling in your joints and muscles versus what you're visually seeing, that's actually resolved in this kind of sensory integration. So we tried this with our drone to address this issue of the drone not being positioned perfectly in space. So as you were reaching, if the drone was slightly offset or drifting, we would apply this sort of dynamic retargeting to compensate for it. And so we invited people to our lab. They tried the e-commerce application, and everyone was able to ultimately touch all the fabrics we wanted them to and pick up the objects we wanted them to. But we found that there were some issues, or even though they were all technically successful in terms of making contact and doing the manipulations we wanted them to, some cases were less successful than others. And we found a few factors affected this. The first one was the speed of the user's hand. If someone was moving really rapidly towards a target, it's too fast for us to actually do any form of meaningful retargeting without them noticing. The other issue is the distance. If someone was already pretty close to the target that they wanted to touch, there wasn't enough distance for us to gradually and gracefully retarget their hand, especially if the offset was pretty large. And the last thing was the speed of the drone, or the velocity of the drone. If the drone always drifted in the same direction, it was actually really easy for us to retarget the hand gradually. But if the drone moved in different directions, you would create this really unusual warped space where the mapping constantly changed. And even though people ultimately made contact with the drone, it wasn't the most pleasant experience for them. So in the next project, actually, our goal was to figure out, can we decide when these cases happen and intentionally decide not to do any retargeting? So instead of always applying retargeting, can we account for these parameters as part of our design and sometimes apply retargeting when it's suitable, and other times accept the fact that basically we're going to have some delay or accuracy problem. So in this project, which was led by Eric Gonzalez, who's now at Google, we're using a tabletop robot here instead of a drone. And so here the idea is, if you want to kind of learn, let's say, a virtual command center, instead of building the whole whole virtual control panel. You can put one knob and one button and one of each kind of piece of hardware on one robot, and the robot can move around on the table to kind of give you the haptic sensations that you would want. The issue here is that depending on your robot, there may be some speed limitation. So if the user touches a button on the very far right and then touches a button on the very far left, the robot may not be able to keep up with the rate of interaction. So to address this, what we did was we used the velocity of the user's hand as well as their gaze to predict which item they were interested in interacting with. And then we also used kind of existing well-known kinematic models of human goal-directed reach, which specifically we looked at the minimum jerk model, which says that if you're going from one point to the other, we tend to minimize the derivative of our hand's acceleration as we do so. And this allows us to actually estimate the time of our arrival. So when the user would actually make contact with the button. So now that we know what button the user is interested in or what virtual target the user is interested in, and we also know when they will make contact with that target. We also know the limitations of our robot. We know how fast the robot can move within that window. And that gives us kind of the boundary of how close, I guess, the robot can get within that time window. So now that we know this, then we can pick the middle point, which is kind of making the human and the robot meet halfway in some ways and start applying retargeting so that when the user makes contact with the virtual button they were interested in, they actually make contact with the robot, even though the robot was not fast enough. And so what this predictive layer allowed us to do was that we knew the time, we knew the distance, and all the parameters that I talked to you about earlier. And this way we could decide when it made sense to apply retargeting and when the retargeting magnitude would be too large or the distance would be too small or the hand velocity would be too large for someone to actually be able to comfortably navigate the warped space. And in those cases, maybe we accept the fact that the robot might be like a second late or 2 seconds late and when it arrives. So the first two projects I talked about was more around reaching. So if you were reaching to touch an object, how do you provide haptics once you arrived at the target? The third project I want to talk about is more on the contour following side. So if you've already arrived at the virtual target, can we help the haptic rendering and perception of rendering as you're kind of touching different surfaces? So has everyone heard of a shape display? Yeah. So shape displays are actuated, basically a matrix of actuated pins. They move up and down and they can render 2.5D surfaces. And here we're using a shape display as a form of haptic device, an encounter type haptic device in VR. This is actually a pretty high resolution shape display, or at least it was back in 2018, compared to some other ones. But still, as you can see, it's very low resolution still. Like if you're rendering something like a hexagon maze, it's actually really hard to follow this maze. Your finger keeps getting caught in these corners, and it's not a very smooth and nice experience. And the limitation here is actually every pin has a motor. So if you want to miniaturize the pin, you have to miniaturize the motor, which drives the cost up. And of course, there's an upper bound there as well. So what we were trying to address here was how can we make this shape display appear as if it was higher resolution than it actually is. And so we were trying to see, can we use some of these tricks of illusory interactions and limits of human perception to make this display feel as if it was higher resolution? So to do this, the first technique we tried, we called angle redirection. So has anyone used Paint before? Microsoft Paint. Some faces, okay. Some faces look like they've never heard of this. But if you've used Microsoft Paint, if you drew back in the day, if you drew a line at an angle, it would be very pixelated. And this is exactly the rasterization problem we are having here. So the idea we had was what if instead of rendering a line at an angle, we render a line that's horizontal or vertical, which would be very smooth, and then we would redirect the user's finger. So this is the same technique that I showed earlier, but instead of displacing the user's hand in space, we're displacing their finger. We're moving their finger up, so they feel like they're going down, even though they're just staying still, basically. And this is kind of our try at kind of anti-aliasing mechanism for a physical display. And so what we did with this technique was we wanted to see how far we could do this before people really start to notice all those forces in their muscles and joints and kind of catch on to this kind of illusion that we were applying. So to do this, we ran a user study. We had people come into our lab and we used the method of constant stimuli. So we gave them very repeated exposures to the same technique. And every time they had to give us a yes or no answer. Were we trying using an illusion or not? And we showed them actually a very extreme case of an illusion, like where they would really feel the forces in their arms and joints and muscles not matching what they were doing, and then a case with no illusion. So they had an idea of what we meant by an illusion. So this is kind of a classic psychophysics curve, if you've seen one before, this S-shaped curve, which tells you the point at which people start to really notice some sensory stimuli, or in this case, the existence of an illusion. So here, the x-axis is the angles of redirection that we tried. So we tried 5, 15, 25, 35, and 45 degrees. These are the lines that we were rendering. And here is the ratio of the repeated samples where one individual participant said that they felt the illusion. So the higher this ratio, it means that it was more obvious that we were applying an illusion. And in all cases, we were applying an illusion. There was not a single case of no illusion. And so this point is kind of 50%. People are guessing. They're kind of just noticing that we're doing some form of remapping with their finger. So more commonly, 75% is used as kind of the detection threshold. This is where most participants across most trials actually knew that there was something going on and that we were messing with their sense of proprioception. So here we found that around 50 degrees, 49.5 degrees, is where people started to really notice, oh, I expected my hand to have like a different angle and forces, and it's not. And so that's what really gives it away in this case. So we ran a second study. This is a different group of participants. We didn't tell them anything about an illusion. We said that we had different shape displays, even though we only had one shape display. So keep in mind, they're in VR. They actually can't see the shape display. So we could kind of play this sort of tricks. And so here it was a method. The technique we used was kind of a 2 alternative force choice task. So we said one display is, you have 2 displays. Tell us which one you thought was higher resolution, smoother, and the one you preferred, even though they were both the same shape display, one without the illusion and one with the illusion. So what we did here was we actually stuck below the limits of detection threshold we found in the first study. So we knew that most people shouldn't notice that there was an illusion. And so we tried different angles below the detection threshold. So I'm going to show you the largest angle we tried. So at 40 degrees, we found that a majority of participants across the repeated trials said that the case with the illusion was the display that was higher resolution. Again, these are the same displays. And also the one that was smoother to trace, and also the one that they preferred. So majority of participants felt that the illusion kind of helped improve their haptic experience with this shape display. So this works for kind of rendering lines, and we were looking at how do we address this for more 2.5D geometry. So here I have a sphere rendered on the shape display. As you see, there are very few pins in that space, and so the elevation change is quite rapid, and my finger is almost getting caught in these pins. So the idea here we had was, what if we blow up the rendering on the shape display and change the user's speed of their finger. So if you're familiar with the control to display ratio CD game, this is basically we're changing people's CD ratio of their finger as they're tracing the space. And so what this gives us is visually, they still see the same small virtual sphere, but physically there are many more pins within that space. It's much more smoother. Your finger doesn't experience as much elevation change, and also we can render more details because we have more pins in the space. So we repeated the same study. Maybe I'll skip some of these, but we did the same study where we found that we could enlarge our renderings by almost 2 times, 1.9, given the dimension limitations of our shape display and the length that we could render on it. And we also did the second study with the 2 alternative force choice task. And here, the highest scale-up factor that we tried below the detection threshold was 1.8. And again, we found that people picked the case with the illusion where the rendering was kind of enlarged on the shape display to be the higher resolution shape display and smoother and the one they preferred. So in the case of angle redirection, we saw the same trend for every single angle we tried. But in the case of scaling, we did not see the same trend. So here's the largest scaling factor we tried. And I'm going to show you the smallest scaling factor we tried, which was 1.2. And you see that we go down from 90-something% to 60%. And this makes sense, right? We are only enlarging the rendering by 1.2 times its original size. So we're not getting the same level of improvement that we would when we render up to 1.8. So this is dependent on how much scaling we actually can do. So in this project, we actually used this idea of angle redirection and scaling up to help improve the rendering, make the renderings appear as if they're smoother, and also allow us to render more details given the same hardware limitations that we had in the shape display. So these 3 projects were all around, can we leverage the limits of human perception to create this illusion of realistic haptic rendering and an illusion of improved performance with these haptic devices that had limitations like accuracy limitations, speed limitation, or resolution. So here's where I felt like every project, we were really not fixated. I guess it was important for us to understand the detection threshold. When does this illusion break? When do people notice that we're messing with their body representation? And what really I want to focus on in the second half of my talk is that we can go further than this. So if you think of this as the spectrum from, it's known as the degree of verity or how true to life the interaction is. We have reality-based interactions. This is most of probably what you've experienced in VR when you play games or other things. There's a one-to-one mapping between your actual body representation, your hand in the real world, and your virtual avatar or virtual representation. And so the examples I showed, we're moving a little bit further across this spectrum where we have these illusory interactions. We're misplacing people's virtual arms and where they're rendered. And you might imagine you could do other things. I could extend the length of your arm and you wouldn't know if, to some extent, to some degree, you wouldn't know. And then beyond that point, you would notice that I'm extending the length of your arm. So there's many other things you could do in the space of illusory interactions. And then what I'm going to focus on next is this idea that even when we have mismatches that are noticeable, that people really notice that there's something going on, that doesn't mean that they're not going to be usable interactions, because our brain is very plastic, we're adaptable, and so we can learn to learn new mappings and remapping in the space. So you can't have your arm be totally in a separate spot in space, and you may be able to learn how to manipulate and control that arm. Or if you're familiar with the go-go interaction, that's the idea that you can extend people's virtual arm and they still will be able to learn the dynamics of how they can control that end effector per se. So in the last two projects, I'm going to talk about this idea of beyond real interactions, the idea that we can leverage what this flexibility and plasticity of the brain to create interactions that we can't have in the physical world. So this is a project Stephanie was talking about. This was around the time where untethered VR headsets were coming out commercially, and it was a very exciting times because you could wear a headset and walk around in VR. And so I was at the time an intern at Microsoft Research with my advisor, Mar Gonzalez Franco, and others, and we were looking at how can we overcome the limitation of locomotion in VR? So the first kind of three projects were around the lack of haptics. And here we were really thinking about why do we have to walk as slow as we walk in the real world in VR? Is teleportation really the only kind of way? Obviously, there are limitations to teleportation. You lose spatial awareness when you arrive at a different place. So how can we move around in space in more efficient, faster ways? So what we tried here was, what if you could turn yourself into a giant and take a few steps and end up on the other side of town, basically. And what we found, we did this study where people had various targets and they had to stop at these targets. And we found that people felt very in control. They actually could stop at these targets very accurately. And this was an experience that you may have, you may experience in an amusement park, or when you're smaller, you have a different scale to the world, and you can still operate and be accurate and feel in control of your movements. So here is me walking around as a giant. And this led to actually a 10 times speed up in terms of my walking speed. And we tried the same thing with the method known as the 7-league boots. This is a technique where instead of turning into a giant, you basically amplify people's movement. So as you take a step, your step takes you 7 times, or in this case, 10 times. Okay, great. Yeah, so the idea here was that how can we think about how basically we're moving in space. So thinking about the input, the sensory input, and users' movement actions in a way where we can design better interactions, where we don't have to come up with these almost like point designs in this design space and just test them and evaluate them with people. Can we have some intuitions of which mappings will work better than others before we try them out? So to do this, we actually went back to this diagram that I showed earlier of how the brain plans and controls movement. And we tried to more explicitly situate these sort of spatial computing, mixed reality systems within this context. So really what VR in this case is that it intercepts your sensory signals. So you can think of it as kind of, you have these sensory information coming in and you're sending motor commands, and VR basically intercepts those signals and overrides some of them, right? So if you're moving your hand, basically we need to have a way of tracking your hand. So there's some sort of sensing and tracking going on to let us know where your biomechanical plan, or in this case, your arm, is in space. And then we can apply some sort of transformation where we map that movement, whatever it is, to some rendering. In this case, we were rendering people's virtual arms in a different place. And what happens is that some of your sensory signals are coming from VR. So in this case, if you're in a fully virtual environment, your sense of vision is overwritten by VR, but you can imagine intercepting other sensory signals like audio or haptics. And there's some sensory information you're still getting from the physical world. So if you're moving your body, you're still feeling your forces in your arms, you're feeling your weight on your foot. And so some aspects of your sensory signals are still coming from the real world. So in the case of the retargeting that I showed, you had proprioception from the real world, and you visually were seeing your hand. And so these types of beyond real interactions, basically what they do is that the rendering is so far off from what you expect, that there's no longer, the brain is no longer able to resolve the conflict between the sensory signals. So there's actually a sensory discrepancy. You visually see your hand totally somewhere else, but you feel the forces in your arm telling you that your hand is somewhere around here, right? So the idea is here to think about how we can better understand what sorts of sensory integrations work better than others and which sorts actually we're not very good at adapting to and our brain is not good at understanding. So in this case, proprioception and vision are at conflict. So going back to this framework, we were thinking about how can we think about this sensory integration as a source of conflict. And so for the giant example, here from the real world, you're kind of figuring out all the sensory information you need to move. You're walking as a giant, and visually you're seeing this miniature world around you, and there's nothing really inherently at conflict here in terms of your sensory signals. Your internal model is kind of just thinking that you're maybe in an amusement park, you're walking around. There's nothing between the sensory signals that are at conflict. But in the case of the 7-league boots, that's actually not the case. So in the real world, you're walking at a certain acceleration. So the linear acceleration in the vestibular system in your inner ear is telling you that you're moving at a certain linear acceleration. But visually, what you're seeing is totally different. So your sense of vision and vestibular system are at conflict, telling you contradictory signal. And this is something that we know is very sick, makes people motion sick, right? So this is what I mean by kind of thinking about what the design is doing in terms of how the input and output are being mapped and what sensory conflicts are we good at resolving versus the ones that are kind of cause issues like motion sickness or other control problems. So in this talk, I talked to you about these ideas of illusory interactions in the specific case of creating haptic sensation, and this idea of can we go beyond reality and create interactions that we can't have in the real world, like walk as a giant or walk a lot faster. And you might imagine doing all sorts of different things in the space of beyond real interactions. Obviously, there are a lot of open challenges with this. We would have to be able to create tools and simulations that allow us to understand what sensory conflicts we're good at adapting to and which mappings are good versus not. And also, I didn't talk anything about individual differences in this talk. Even something as simple as detection thresholds, we saw huge variation among participants. If you're a ballerina, you have a very different sense of proprioception than I do, someone like me who sits behind a computer all day, right? So people had very different thresholds for sensitivity to these things. And obviously, huge variations in range of sensorimotor control as well. So how can we capture potentially these things in real time and adapt to those individual differences, and hopefully in a way that's privacy preserving, that we can adapt to these different people's detection thresholds or the right sensory mapping for different individuals that works best for them in real time. So maybe I'll spend 2 more minutes. I want to leave some time for questions, talking about where my lab is headed. So a lot of this stuff is things I've done during my PhD. I'm still excited about some of them, but my lab as a whole, we're kind of moving across this continuum of virtual to reality. So we're moving away from VR, and we're kind of doing more work in the augmented reality space, both pass through AR. So if you still can see the world around you, but we still have some of these controls of overwriting your sense of vision through this pass through, as well as other form factors like glasses, and thinking about what does AR mean in this multisensory case of thinking both from audio, haptics, visuals, and other sensory systems. So kind of moving towards AR as a whole. And then also moving from some of these low level perceptual things to higher level cognitive tasks. So kind of expanding in that way. I used to say we're shifting, but someone said I should say I'm expanding. I like that. So we're expanding to this kind of area of AR at higher level cognitive tasks. And we're really thinking about this notion of intelligence augmentation, which is very well known in HCI, and how can we apply it in the situated context where people are on the go, they're walking, they're talking, they're interacting, and they're present in their physical spaces. How do we prevent VR from being this kind of screen that's now up on your in front of your eyes, but more so about an intelligent augmentation tool that really helps you when you need it. So we're thinking of how do we show the right thing at the right time to the user while being very minimal and timely, using the right sensory modality so that we don't interrupt people, that they can still be attentive to their tasks while receiving the information that they need. Also thinking about input on the go as you're walking around, what's the best form of communicating to a system or agent or in a way that's low effort. And we're really thinking about this in a probabilistic way. How can we think of all the different signals coming in and the uncertainty that are associated with all of this? And how can we make sure that as we do so, we consider privacy of the users? And as you might imagine, just using a controller, your mouse is you get all sorts of ads just from these companies knowing where your mouse is. Can you imagine not only having access to your gaze data, but also your movements and reactions and by other signals, heart rate, other things. And also all of these are personally identifiable in some ways. So thinking about that more in the context of inputs. And also how can we use spatial computing as a platform to interact with intelligent systems that are situated in the space, like robots, IoT devices. Can we make these more personalizable, predictable, explainable, and also safe so that we can coexist? And we think in my group that spatial computing is a good platform to facilitate that due to its spatial nature. I want to thank my PhD advisors and mentors and collaborators at Stanford. And with that, I'm happy to answer any questions.